Alrighty, so we're on to 7.3, day 2, and we're looking at multivariable linear systems again. In day 2, we're going to look at non-square systems of linear equations. So what happens when the number of equations is not equal to the number of variables, a little bit more unique situations. And then we're going to look at some 3 or more variables to model real life problems. So when might be some situations that we would see these more complex linear systems. So we're going to start right off with just what a non-square system is, and we've kind of alluded to that earlier in the chapter as well. In a square system, think about what that could mean in terms of number of variables and number of equations. If it's a square system, that means the number of the equations, so how many equations you have, is actually equal to the number of variables. So you have the same number of equations as you do variables. So if there's 2 unknowns, we have 2 equations. If there's 3 unknowns, we have 3 equations. Things work out really well. We can get those unique solutions. If a system, though, has more variables, the system cannot have a unique solution. So we're not going to be able to find like a single ordered pair or ordered triple. We just cannot find that. We don't have enough equations or relationships to be able to solve for that. So we're going to have a unique solution. It won't have a unique solution. So non-square just means that the number of variables is not equal to the number of equations. So think about systems that maybe have 3 unknowns and only 2 equations. That would be a non-square system. All right, so let's take a peek at what that might look like. So we're going to run into these scenarios where we're not going to have a unique solution. So take a look at example 4. So this system of equations has 1, 2 equations, but notice there's an x, a y, and a z. So if you think about our strategies of Gaussian elimination and row echelon form, it's going to be really hard to back substitute because we don't have anything to work from. We have 3 variables, 2 equations. That's not going to work out so well for us. So what we have to try to do is kind of go through our process. We're going to try to eliminate the x, get it down to that 2 by 2 system. But then we're going to have one of those solutions like we did yesterday when there was infinitely many. We're just going to have one of our variables in terms of the other 2, and we're going to have to be able to solve from there. So there's really not going to be any unique way that we can come up with a single ordered triple to solve this. So let's see what we can do though, to just kind of start how we normally would. So if we follow our row echelon form thing, we want leading coefficient of 1. So I'm going to try to eliminate the x in that equation 2 and see if I can get down to a system that I can solve. So let's see what happens to do that. So let's think about step number 1 here. Let's see if we can eliminate the x in equation 2. All right, so think about how you might do that. Make opposites, add them together, see what happens, and then come back and see if you match my work. Alrighty, so to eliminate x in equation 2, I noticed that they are already 1, so I just need to make them opposites. So I multiplied equation 1 by -1. So I'm going to multiply everything. Don't forget the constant on the other side. Gave me opposites for everything. And then I went ahead and added that to equation 2. So add, and then we have our new equation 2. Double check my arithmetic there. So I have a new equation 2. So now my system of equations, I'm down to, I have an x, a y, and a z in equation 1. And then I have a -3y minus 3z. Sorry, I'm trying to write with my pen on my touchpad here, so it's kind of crazy. We have our new system of equations, our equation 1 and equation 2. Now, if you follow that Gaussian elimination idea, we're trying to, or a row echelon form, we want the leading coefficient to be a 1, which is pretty easy to accomplish in equation 2 here. I'm just going to take care of that really quick. So step number 2, I'm going to get a 1 coefficient in equation 2. That's just to make it a little bit easier to deal with. Looks like I just need to divide everything by a -3. So we can take care of that pretty quickly. Go ahead and pause. Think of it, divide by -3 or multiply by -1/3, however you want to see it, whichever way is easier for you, just to get a little bit easier equation to deal with. So we get that leading coefficient of 1. So that would be y plus c equals what? -1 for our new equation 2. So our new system of equations then, our original x plus y plus z equals 1, and then we have y plus z equals -1. So you can see our issue. I don't have another equation to work with. It's really going to be hard to back substitute to be able to solve. This one actually ends up working out not so badly, but we kind of have to follow that procedure where what we did with our day one, we're going to solve one of those equations, so the second one, because it only has two variables, for y, and then we can back substitute that into the first equation to at least get an equation that only has x's and y's, just trying to work backwards and see, but that's where we're going to have that linear solution left. We're not going to be able to get rid of all the variables, but we will be able to write everything in terms of one variable, and then we'll be able to have a solution for all those points that make those equations true. So I'm going to go ahead and do that like we did in our day one here. I'm going to go ahead and solve. So we'll call this step 3, I guess. I'm going to go ahead and solve that equation 2 for y. And then I'm going to back substitute. So if I solve equation 2 for y, that would just be moving the z over. So opposite of z minus 1. And then I'm going to go ahead and back substitute. So I'm going to plug that in that y value into the first equation for y. So I'm going to be substituting that into that first equation for y. So the hopes of that I should be able to get it down to just 2 variables instead of all 3, and maybe that will help me get that non-unique situation, that linear solution. So we're going to back substitute into equation 1. So we're going to plug that in. So our new equation then, scooch down here a little bit so we can see. I'm going to rewrite that equation 1, so x plus, but now instead of y, I'm going to substitute in what y is equal to. So opposite of z minus 1, keep finishing off the rest of the equation here. So plus z equals positive 1. Now this is kind of a unique situation, or kind of quirky. What happens in this one, it does not always happen, which we'll see in the next example. But when I put these like terms together, let's see what happens. Our z's end up adding to 0. They're opposite. So we end up with just x minus 1 equals 1, add the 1 to the other side. We actually get a value for x. So we have a solution for x. X is 2. So when we think about our solutions, one of the values actually is numerical, which is awesome. Now we just need to figure out what the rest of those solution sets are going to look like. There's not really much more that I can do. If I plug that 2 back in to the original equation for x, you're going to see that you end up getting the exact same equation as number 2. So like I have really all I can do with those different solutions. So I'm going to plug this back in. All right, so let's do our solutions then. So I'm going to do what I did before. We're just going to say let A be any number. So just make this appropriate for whatever values we need. So A could be anything. So we're going to let A be any number, and we're going to say A is our Z value, just to make it a little bit more global here. It doesn't have to be an X, a Y, and a Z. So I'm going to go back and I'm going to write my ordered triples now. So I know that the X value has to be 2 because that's what we solve for. My expression for Y is opposite of Z minus 1. So if I let A be that Z, that means my Y value would be opposite of A minus 1. So all my Y's are going to be of that format. And then my Z value is just going to be that A. So I have my solutions, my non-unique solutions, right? I'm not going to get a single order triple. I'm going to have all the values that meet that scenario. So this one was kind of nice. I did get it down to actually a single X value. That doesn't happen all the time. Sometimes you have to write X in terms of Z as well. But if we can get all of the equations in terms of one variable, like we did in this case, we got everything in terms of Z, we're going to be able to solve and find that solution. So a little bit more involved situation sometimes when we're looking at those values. All right. Now we're going to take a look at some applications. So those non-square ones can be one way that we can look at solving more complex things. Now we're going to look at multivariable situations where some applications. So one thing is height, looking at the height of an object. So think back to your maybe initial like parabola kind of things. If we have something that's going up into the air and then coming back down, like the flight of something that's in motion like this. This is a really classic example of when we might be able to use like the position data. So if we have some locations on the curve, we can use those positions, those ordered pairs, to help us write the model that would model that flight path or something like that. So if we're looking at like GPS or trying to figure out your position, so global positioning, being able to do some curve fitting, so being able to describe real life things like if we have a rocket going up and coming down or anything that goes in sort of that parabolic motion, basically solving anything that can be quadratic, so quadratic equations. Going from data though, which is in real life how we really deal with these, right? We're not just given, hey, here's a quadratic equation, deal with it. No, we have like real data points and we're trying to do those best fits. And why do we do best fit curves? So we can use that equation to help us predict what's going to happen next or be able to find those locations. So it's really important to be able to model those too. So here's the position curve, which is a really cool one. So we're going to be using some variables here. So it's a quadratic equation, but S is the height. And we're just saying in feet for this one because we're using acceleration in feet per second. So that's why we're using feet. And here's what the equation looks like. 1/2 times A. A is the acceleration in feet per second squared. So it's our acceleration value times T squared. T is time in seconds. So it's moving quick. And then plus V sub 0. That is the initial velocity. So at time 0, that means when you start looking at wherever the flight path is or whatever the height is at time 0. So that T sub 0 means the initial times T, and then plus S sub 0. And S sub 0 or S naught is the initial height. It's where it starts. So say you're hitting a baseball and the height that you hit it at is 3 feet. That would be the S0. It's where it starts. So it'd be like wherever your initial location is on your parabola before it starts moving. That would be your S0. And think about that. If the T values were both 0, y-intercept, that would be your S sub 0 value. So it kind of makes sense. It's that location. So if we think about graphing this, it would be that location where we start. So it's that initial. So this is just a quadratic equation. In order to write a quadratic rule though from data, we need to have the same number of variables as we do equations, right? So we need to have a square system. So think about this. Look at how many variables we have. We have an S, we have a T, oh, sorry, updating my computer there. We have an S and we have a T and we have that V0, like we've got the A, we have all these different things that we need to know. We need to have enough equations to be able to do that. So we're gonna take a look at a couple examples to be able to do that. So first of all, we're gonna model this just with a basic system. So not really thinking of it as an application. We're just gonna look at just a parabola. And then once we have that sort of conquered, then we'll put it into the application setting so you can see something that's a little bit more involved. All right, so let's start with kind of a basic example of this. So we need an S value we need to figure out, an A value, we need our acceleration, and we need a T. Usually the V0 and the S0 are things that maybe you know going in. So we have kind of 3 variables, and hopefully we can have 3 equations then. All right, so we're going to try to find the model. So notice how they're writing it. So we're going to kind of change this out for like the real life situation. The Y is kind of like our S in that previous one. So this is just written in a little bit more not application based. The A is still, you can think of it the A, it's the acceleration. Your X is like your T. So when you see X squared, just think of T. And then the B value and the C value are acceleration, or pardon me, the initial velocity, the V0, and then the height at the starting value. So the V0 is like your B and the S0 is like your C. So it's just replacing the letters back to what you're familiar with. But the 3 things that we need to kind of figure out are what those S and T and acceleration values are going to be. All right, so how can we figure out the quadratic equation? I have all these letters going on. Think about what you know if you know ordered pairs, if you know points. So if you know X's and Y's, I'm just going to go ahead and kind of fill these in. You have specific places on your parabola that you know, and we know 3 of them. So if we are looking for 3 unknowns to try to write this equation, so in this case, the 3 unknowns that I would need to write a parabola, I don't know the A, I don't know the B, and I don't know the C, but once I know those 3 values, gosh, I'm gonna be able to write the equation, right? So by knowing some information about heights, like the S's, the X, and the Y's, I can be able to solve for the A, the B, and the C as long as I have 3 equations to get that unique solution. So I need 3 equations. Can I get it from these ordered pairs? That's what we're going to try to figure out. So we're going to see if we can do those and get some different information. So let's start with this. What about this point, -436? That's an x and a y. What if I go ahead and put in those values into this general form of the quadratic? So I have 36 equals a times -4 squared plus b times -4 plus c. Now, I know that doesn't look like it helped me a whole lot, but if I simplify that equation down, so let's see if we can simplify that a little bit and write what that would be. That would be 16 times a minus 4 times b plus c is equal to 36. That's an equation in 3 unknowns. Awesome, that's one equation, but I need 2 more. Well, where am I going to get 2 more equations to write this? Well, how about using the 0, 8, and then I can use the 2, 0. Now, what's awesome about having, oops, I want this one next. The 0, 8 is that's the y-intercept, isn't it? 0, 8. So that's going to give me some really good information. So again, I'm going to go back and just put in the x and the y into that original standard form of a quadratic here. So my y value is 8. I'm going to plug in 0 for all my x's and see what I can get for an equation. Now this one is awesome because look what happens to both the a term and the b term, nothing, right? Because when it times by 0, so I end up my second equation is going to be great. This is going to be easy to do our back substituting because I already know what c is. That's my initial height. That's my y-intercept. It's the S0, right, of the application. All right, so let's look at the last point, see what I get from this one. So if I plug in these values, so 0 for y, and 2 for x. So we're going to plug in 2 everywhere we have an x. I'm going to get a third equation. So simplify that a little bit here. Plus 2b plus c. I have a system with 3 equations and 3 unknowns. I should be able to solve then for the a, the b, and the c to be able to write that quadratic equation. So my first equation, I'm just going to write the variables on the other side. So that's my purple one there. So the 16a minus 4b plus c equals 36. That's my first equation. And then my second equation, I got c equals 8. And then that third equation was 4a plus 2b plus c equals 0. All right, so I have a system, 3 equations, 3 unknowns. So this is a great system, like we said, because c is equal to 8. I already know that last one. So I can go ahead and back substitute that c equals 8 into both of those other equations right away. You could also just follow kind of your regular Gaussian elimination kind of thing, and we could kind of switch the order, get those leading coefficients in one. It really just depends on what makes the most sense to you for how you want to solve. So I'm going to go ahead and kind of follow our row echelon form and get it into that, and so we can do our back substituting and solve. So I'm going to use some of those equivalent steps that we've talked about before. I'm going to switch the order of 2 and 3. So just write it in the right order here. So 16a, 4b. All right, I think I'm going to rearrange a little bit here just to make this a little bit easier so we can rearrange our order. So I think I'm going to make this equation number 2 just so I can have that bigger or smaller number on the top. Equation number 1, I'm going to make my 4a plus 2b plus c equals 0. You can do this in whatever order you want, so it really doesn't matter. And then c equals 8. All right, so there's my system. Actually, probably should put the brace there. All right, so we're going to go ahead and kind of follow our Gaussian elimination here, get row echelon as much as we can to try to solve and work backwards to see what this parabola is going to look like. So I'm going to go ahead and eliminate. So for my step 2 here, I'm going to eliminate the variable a from equation 2 so that I can kind of keep working towards that row echelon form. So I'm going to eliminate the a in equation 2. So that's my goal. So think about how you could do that. What could I multiply by the first equation? What should I add? So go ahead and pause the video. Go ahead and see if you can eliminate the a in equation 2, and then we'll check in and see how we're doing. All right, so remember our quest. We're trying to eliminate the a variable in equation 2. So I went ahead and multiplied equation 1 by -4, and then add that to equation 2. So everybody can just double check my arithmetic. So multiply, remember multiplying everything through, then adding that to our equation 2, and then I got my new equation 2. So my system is I have those 3 equations, and I'm going to be able to start back substituting. So my new system over here on the side. Now, technically row echelon form, we get leading coefficients of 1. Sometimes people, if they're going to be a lot of fractions and things, you can just go ahead and start back substituting right now, which I think I'm going to do because I don't want to have to deal with the fractions, and that's totally fine. So I think that's my plan. I'm going to go ahead and start back substituting. So I already know that C is 8. Now I'm going to back substitute and see if I can find B, and then I'll back substitute again and see if I can find A. So go ahead and take a moment and pause the video. Go ahead and back substitute and solve for the B and the A. And we'll check back in. All right, so I'm going to be putting C into equation 2 there. So I'm going to go ahead and solve for B. And so hopefully that worked out well for you. It looks like, oops, I'm writing my answer for that already, 36, pardon me. So it looks like I'm coming up with B equals -5. Double check and see if that looks good for you too. And then now I'm going to plug that -5 and the C equals 8 back into that equation 1. So I'll be able to put both of those values back in to that first equation, and I'll be able to solve for A. So go ahead and pause the video, try that, see what you come up with for A. Alrighty, so I substituted the -5 in for B and the 8 in for C, and I got A equals 1/2. So it looks like we have all 3 variables that we need to write our quadratic equation. So remember what our goal was. I know it seems like, woo, that was a long time ago. We're trying to find a quadratic. Again, getting ready to do some of those application questions, or when we're trying to find position, which are quadratic, we're looking for the parabola that goes through those 3 points. So we plug those in for X and Y. We got 3 unique equations that we could solve for those 3 variables. So now we have the coefficient for the square term, the linear term, and the constant. So it looks like our quadratic equation is going to be Y equals 1/2 X squared, because A is 1/2. And then minus 5x, because our B value, it was at -5, and then plus 8. And that is our quadratic equation. Now we're going to do a couple of things here just to kind of check our answer and see if this makes sense. I'm going to have you actually plot these points. So 0, 8, -4, 36. I know it's going to be a little bit like not to scale. I'm going to go by 2s here. So like -2, -4. Oh gosh, it's going to be way up there. So somewhere up here. 0, 8, so 2, 4, 6, 8, and then we've got 2, 0. So basically what we're looking at, is probably going to be even higher, but we're looking at the parabola, ooh, that does something like that, and we're looking for that best fit. That was terrible for the graphing, but just to give you an idea. So there's your 0, 8, there's the 2, 0, so I'm going by 2s. And then our -4, 36 way up there somewhere. That's going to be the graph that we're talking about. So I'm going to have you go ahead and grab your graphing calculator and then put this equation in to your Y equals. All right, so I typed that into my Y equals. I just did 0.5 instead of the half, but either way. And take a look at the graph. So that's the thing that we're trying to show. Now, if you go to your table, you should be able to find those 3 other pairs. You can probably see these 2 right on your graph right there. So we have the 2, 0, the 0, 8. We'd have to zoom out a little bit to see that 36. So I might even, just for illustration purposes here, have my scale go up to 40. Sorry, I have to go up and down here. And then see what that looks like. All right, so that you can see the -4, maybe, well, maybe can't see that yet. I have to go up even higher there to be able to see that. Oh, I did the X in the wrong way. That's why. Oh dear, needed to be the Y. It's one of those days. Maybe you guys have those days too. So it needed to be the Y my max. That needed to be 40. Silly. All right, so let's take a peek at that and see if that looks a little bit better. So we're going to go to our graph. So we have our 2, 0. We have our 0, 8, and then -4, 36. But again, if you go to your table, you can probably see some of those really well. There's your 0, 8, 2, 0. If I go back to -4, there's my 36. So I know that I'm writing the equation that fits those 3 points. So it's a really cool way to kind of double check. So we can double check what those values look like. 3 unknowns, 3 equations. All right, so let's take a look at it from an application standpoint. We're going to take a look at GPS. So kind of a cool application. We're going to graph this one too once we're done. So GPS basically is a way that you can start out as navigation for military, but now everybody uses GPS. We all use it when we're navigating and doing everything. That's how our Google Maps and everything, all that good stuff. So basically, it's a way to figure out exactly where you are at any point in time. And so what we really have are these three different variables. We have our distance, which is that S that we talked about before. So we're going back to kind of those definitions of that application. So I'll go back to that list here. Oops, that's not the list. Where's my list for my application? Oh, pardon me, it's right down here. So the S is the distance, or pardon me, the height, and then A is the acceleration in feet per second squared. T is the time in seconds, and that V0 is the initial velocity, and the S0 is the initial height. So again, if we know three different positions, we should be able to write three different equations and be able to figure out the model that best fits the object and the position that it is at any point in time. So that's how we can use this global positioning idea with a real life kind of scenario. So that's what we're gonna be looking at. So here's our situation. So I'm gonna give you three different positions. So the height at time of 1 second was 104 feet. At 2 seconds, it was 76 feet. And then at 3 seconds, it was 16 feet. So I'm going to be having, in this case, my S is going to be in feet, and then the height in feet, and then the time is going to be in seconds. So just so you can keep track of your units here. So basically what I have then is three different locations that I'm going to be able to use to write this equation. So now look at what I should be able to find then. I should be able to get these three values with, if you think of like the general form for a quadratic, like y equals ax squared plus bx plus c. I know all the variables are different, but you're looking for the a, the b, and the c, the coefficient of the square term, the linear term, and the constant. So we can find all those. So what is it? What's the acceleration? What's the initial velocity? And what is the initial height? All of those we can kind of model and be able to then, once we have the model, remember, we can use it to predict where is its position in the future. So that's really where the big things come into play. So first order of business, we need to write these three position equations. So we're going to do each of them. So we're going to do all three of those scenarios. All right, so let's start with scenario number one. When S is 104 and T is 1. So all I'm going to do is substitute in 104 for S, and I'm going to put in 1 for T. So I'm going to put in the values for each of those. All right, and I'm going to go ahead and simplify right away so I can kind of make this a little bit easier to be able to read. So this one then would be, and if you're okay with this, I'm going to write the constants ultimately on the right-hand side of the equation. I just think that's a little bit easier to deal with. Okay, so 1 squared is just 1. So that would be 1/2 A. 1 times V sub 0 is just V sub 0. And then S sub 0, and then that's equal to 104. So that is equation number 1 in our system. I'm going to do the same thing on the change colors here. So this is going to be equation number 2. When the height was 76, that was after 2 seconds. So again, same idea. I'm going to substitute those in. So 76. And then I'm going to plug in T is 2 all the way through. And then I'm going to go ahead and simplify that equation as well. Oops, forgot my A, pardon me. All right, so I'm going to go ahead and simplify that, and then I'll have my equation 2. We'll do the last thing, same idea for equation 3. So double check my arithmetic, make sure that looks good for equation 2, and then I'm going to do the same thing for equation 3. All right, so for the third equation, I put in height of 16 feet and the time of 3 seconds. And I simplified that, and I did, again, flip-flop the two sides of the equation just to make it a little bit easier to look at. So it looks like we have now 3 equations with 3 unknowns. We're solving for the acceleration, the initial velocity, and the initial height. So that'll be our system that we need to solve. And we know how to solve these now. It's a square system, right? We have 3 equations, 3 unknowns. We're going to try to do that Gaussian elimination, see if we can make things a little bit easier, kind of clean up the equations a little bit and see if we can get it into row echelon form and then be able to solve. So it's all a whole bunch of that. So everything from here on out is just a whole lot of algebra. Just got to be really careful on our arithmetic and make sure we're okay. And then we'll be able to do this equation for the position. One thing that might be helpful looking at these 3 equations, is the two that have the 1/2s in there are going to be kind of dicey to deal with in terms of like row echelon form and trying to simplify. So one thing I might suggest, again, any multiple, it's an equivalent equation. I might suggest for this top purple one and the green one, maybe multiplying everything through by 2. So kind of times by 2 in both of these to get rid of all of the fractions or the one fraction in each of them, just to make the numbers a little bit easier to deal with. So I'm going to do that as I copy these down. So I'm going to multiply everything in this first equation by 2, both sides, everything in this green equation by 2, and then I'm going to have a system that might be a little bit easier to deal with. So that would be an A then, a 2v sub 0, a 2s sub 0, and then a 208 on the other side, just to make that a little bit more palatable to deal with. That middle equation, the red one, actually seems fine. Nothing too obnoxious with that. So we're going to leave that one alone as our equation 2. And then equation 3, again, I'm going to distribute that 2 through just to make this a little bit easier. So a 9a and a 6v0 and 2s0, and then double it over there would be 32. All right, so we're going to do row echelon form on this. Again, you don't have to do that, but that's easier. Take a look at the first equation. It has a leading coefficient of 1. That one's good to go. So what I need to do is eliminate the a in equations 2 and 3. So I need to undo. So I'm going to multiply by opposites, add them together, get a new equation 2 and a new equation 3. So I'm going to have you go ahead and pause the video, make opposites, get your new equation 2 and 3, eliminate the a. All right, so remember our quest here. We're going to try to eliminate a in equation 2. So I started with that one. We'll do the same kind of thing for equation 3. So I multiplied that equation 1 by -2 to make an opposite. Which gave me that. Double check your arithmetic. So I just distribute everything, including that constant on the other side, don't forget. And then I added that to equation 2 and ended up with this for my new equation 2. So I have no a left in there at all. Now I'm going to do the same thing and eliminate the a in equation 3. So same idea. I want to do it for equation 3. So I'm going to make opposites for that one and go ahead and eliminate the a. All right, for the next part of the quest, we're trying to eliminate the a in equation 3. So I'm doing that next part in green just so we can have a different idea. So I multiplied everything in equation 1 by -9. So that's multiplying by -9. Distribute that through. So kind of double check arithmetic there. Then add to equation 2 or 3, pardon me, and then we got our new equation 3. So again, I eliminated the a in both of them. So we have our new system that now I can keep working forward here to do my row echelon form. So I have a new system. The second 2 equations no longer have the a. So I'm just going to go ahead and recap. So here is our new system. So now we're going to keep going. I'm going to try to eliminate the V0 in equation 3. So I can do that back substituting that we love so much. So I'm going to go ahead and as my next step here, so I don't even know what step we're on, whatever we're going to name it, like step 2, I guess. So step 2, that was a big step 1. We're going to eliminate the V0 in equation 3. So we're going to do some get opposites there, multiply, add, so we can then head towards our back substitute. So go ahead and see if you can eliminate the V0 in equation 3, multiply by what you need to in equation 2, add them up, and then we'll get our new equation 3. Alrighty, so eliminate V0 in equation 3. I multiplied equation 2 by -6, and remember all the way through, even the other side. Got my new equation, so double check your arithmetic, and then add, and then we're down to our new equation 3. Yay! So now we have that our new equation 3. Now we're off to the races with the back substituting. Now again, we should technically, if we're going to do row echelon form, have coefficients of 1, which I'm just going to kind of do as I go back through this. So technically now our new equation 3, once I divide by 2, just to get that leading coefficient be a 1, I know that my S0, so my initial starting height, is 100, so 100 feet. So I have that. So now I'm going to be ready to go ahead and back substitute. And again, I could try to make that middle equation have a leading coefficient of 1. I'm not sure it's really worth it again. I mean, you sure can. You can divide everything, and I guess I'll show it that way just to see that, but you could just plug it in as is. But I guess that's kind of your choice. You're going to be able to get there either way. So if you think of this as your new system, technically, we should get a leading coefficient of 1 here. So in this equation 2, technically, we can multiply by a half just to make sure that we get that into row echelon form. Again, if you're just going to be solving anyway, it's not a huge deal. But if it makes it a little bit easier for you, you're going to have to do it eventually, but if that makes it a little bit easier for you to see it in that middle equation, fantastic. So now we are ready to back substitute. I forget what step we're on to. Step 3, I guess. That doesn't really matter either. I'm just trying to keep us organized. So we're going to back substitute and we're going to plug things in so we can find our other values. So we're going to put 100 in, and technically, I guess I should put it in that one so we can find our V0. So we're going to substitute in that 100 and then solve. So go ahead and take a moment to solve that. So you can see what that value should be here. And it looks like that would be what, 150. So V0 would be, looks like 20. And then we're going to back substitute again. So now that we know those, we're going to do one more back substitute to find our A value. So we're going to plug both the V0, which is 20. And so we're going to be plugging that in there. And then we're going to plug that 100 in there, and we're going to be able to solve for A. So we're going to substitute into that first equation. So the A plus 2V0 plus 2, I think it was, yep, 2S0 equals, what was it, 208. We're going to do that substitution. So I'm going to replace, and then we should have our A. So pause if you want and go ahead and do your calculations, and we'll see what you get. All right, so double check with me. I ended up with A equals -32. So we have our 3 values. Okay, so what does this mean? Well, we just wrote the quadratic that models the exact position of this object at any point in time. And we can then, once we have the equation, we can project and see what it would be moving forward. So what would it be after more period of time? So we just figured out the A, the V0, and the S0. So I'm going to go ahead, I'm just going to write it up top here because I want it to be up at the top so we can see it. So the position of this particular object when it is in motion here, when it is flying, is 1/2 times our A, and our A value ended up being -32. So we're going to do that calculation quick, which will be quick, and then T squared, and then plus the V0. Our V0 was 20, and then that's times T, and then plus our initial starting height, which was 100. All right, now the only other kind of cleanup thing there, that would be a -16 out front with our T squared. So -16 T squared plus 20T plus 100. Okay, so I want you to think about what that means then, going back to our description about what each of those different objects are telling you. So let's talk about what each of those pieces are. So A is the acceleration in feet per second squared. So that is -16 feet per second. T is the time in seconds. Oh, pardon me, we know that. Yeah, so V0, the initial velocity. So what is our starting velocity? So let's take a look back. If V0 then is 20, that would be 20 feet per second. So that would be our starting velocity. And then the 100, what does the 100 mean? Well, that's our starting height, so where it started initially. So I want you to kind of sketch and see what this looks like so we can think about what that picture would be. So I have a little graph paper on here, so you'd be able to do that. We're also going to put it in our graphing calculator. But if we have height as our vertical axis here, and then we have time, and our 3 data points we have at 1 and 2 and 3. So 1 and 2 and 3. And then what's the biggest height that we had this going up to? Looks like 104. So I'm just going to do a scale going up. That would be something reasonable that we'll be able to fit. So I went ahead and plotted the points here. So we have at 1, it's 104, 2, it was 76, at 3, it was 16. What we just figured out is our initial height at time 0. So that's what S sub 0 means, like at time equals 0. What was that initial height? We solved for S0 and we got 100. So that means at 0, it would be 100. So that point would be right there. So it looks like our parabola went up and then is coming down. That is not very well drawn, but again, I'm trying to do this with my pen on my laptop, so I apologize. We could also figure out the 0, like when it would hit the ground. That's another cool thing that we can do now that we have the quadratic equation. So I could ask you lots of follow-up questions. What would the height be after 3.2 seconds? Well, now we have the model, we can put that in. When will it hit 0? So we're going to take a look at that using our graphing calculator. So that's the equation that you just came up with, was that parabola. We're not seeing the other half of it, right? Because that would be negative. We're not going to go negative for time, but the other part of the parabola would be over there. All right, so let's grab our graphing calculator, get this equation in there, and let's take a peek at some things. All right, so I have my equation in there. I am going to set up the window for some success here, just to make sure we can see what we want to be able to see. So I'm going to start at 0 for x, and then I'm going to go up to maybe like 4 seconds. And then we're going to go up by ones. My y's, I'm going to start at 0. I'm going to go up to like 110, go by tens, just so I'll be able to see things. So just a little bit better picture. So 0 to 4 and then 0 to 110. So we can see that picture. Now, again, some of the cool things that we can do, you can actually look in your table and you can see the values that we had. So we have 104, 276, 316. By 4, it's negative. So if we remember our intermediate value theorem, we know that somewhere between 3 and 4, there's going to be a 0. How do I know? Change in sign. We have that sign change, right? So 16 to negative 76. So we know there's going to be a 0. It's going to cross. We definitely could use our graphing calculator to figure out that. We could find our 0, which is kind of cool. So some other applications you could do. So now that we have the model, how long is it going to take this object to hit the ground? Well, we sure should be able to figure it out. So that's to the left of it for sure. And then we need something to the right of it. So I'm just going to arrow over. Come on, little cursor dude. Let's get your arrow to the left of it or to the right of it. And then we'll do our guess. That's close enough. Sorry, I have to keep scrolling back and forth because it doesn't all fit on the screen here. Yeah, so our 0 is at like 3 point, oh, look at, I said 3.2 seconds. That's when it hits the x-axis, so we can figure out when that object would hit the ground. So that's just one thing we could do. We could figure out anything else now that we have the model. So that equation is where all the power is. So it's really important to be able to know, like, what can I do with this? All right, so let's do our interpreting of results so we can actually write out what this means. I just need a little bit more space at the bottom here. All right, so see if you can write out a sentence that describes then what this model is actually telling us. So this is your equation. What does that mean? So go ahead and pause the video and see if you can write out, what does the A, the negative 16, the 20, and the 100 stand for? So acceleration was negative 16 feet per second squared. The initial velocity was that 20 feet per second, and the starting height of this object was 100. So many different things that we can do. So it's a really, there's a lot of algebra, right? Look at all that. Ooh, look at all the work we did. Just have to be careful. It's the same process every time. And we're just really looking at different ways that we can interpret these linear models.